In modern physics, two great frameworks shape our understanding of the universe. General relativity, which describes gravity as the curvature of spacetime, and quantum field theory, which views reality as a web of fundamental fields and excitations. Early in the 20th century, Carl Schwarzschild discovered a simple but profound solution to Einstein's equations. It revealed a critical radius around a mass, now known as the Schwarzschild radius, where gravity becomes overwhelmingly strong. If enough mass is compressed within this radius, space-time bends so severely that even light can no longer escape. This invisible boundary is called the event horizon, the ultimate point of no return. At this boundary, our usual classical description of matter begins to fail. The familiar notions of particles and forces lose their meaning, and gravity starts to dominate in a radically different way. Quantum field theory offers another lens. It tells us that what we call particles are localized excitations of underlying fields, carrying energy, momentum, charge, and spin. In other words, physical information. This raises a deep question. Is there a fundamental limit to how much information can be stored within a given region of spacetime? Our intuition suggests that the answer should depend on volume. Larger regions should allow more possible configurations, and therefore more information. But when we cram too much energy or too many degrees of freedom into a region, gravity responds in a dramatic way. The region collapses into a black hole, and its interior becomes hidden behind an event horizon. From the outside, a classical black hole appears surprisingly simple. It can be fully characterized by just three quantities: its mass, its charge, and its angular momentum. Yet every bit of information that fell in seems to influence only the horizon's properties. This suggests that the information content of the black hole is tied to the surface of the event horizon, not to the volume inside. Black hole thermodynamics tells us that the entropy, the measure of information, scales with the area of the horizon, not its volume. This is the key clue behind the holographic principle. In this view, the Schwarzschild radius is not just a gravitational threshold. It also marks an information bound. If the information inside a region exceeds what its surface area can encode, spacetime itself must reorganize, creating a new horizon. At this frontier, curved spacetime and quantum fields can no longer be treated separately. The geometry of spacetime and the information stored in quantum fields become deeply intertwined. Near such extreme gravitational boundaries, matter is no longer just mass in motion. It behaves as structured information, constrained by the geometry of the surface that contains it. A black hole is therefore not only an astronomical object, but one of the densest information systems in nature. Its horizon encodes the history of everything that has crossed it, in a way we are only beginning to understand. Exploring this intersection of gravity, quantum fields, and information may guide us toward a complete quantum theory of gravity, a theory in which spacetime itself emerges from deeper, informational degrees of freedom.